So we are at about the end. I about to attempt part 2 of the freeform timed assessment. I don't know what question I'll get. If I get the question that I have done before with the double slit kind of proof thing, then I'm gonna view that as a sign and just end the session here. If I get a question that I haven't done before, then I'll work through it. It'll be another 20 minutes. So let me start. Yeah, I gotta work through it. It's about double slit thing, but actually it's not about the double slit thing. It's about wave equation stuff. So let me read. In the 19th century, conclusive demonstrated light is a wave. Please consider that explore the wave nature of light. Okay, all right. As qualitatively as possible. All right, good. Since light is a wave, satisfies wave equation for a plane wave. Okay, yeah. Show that the electric field described by following. If you're using, so let me use complex representation. So let me just type everything out, and I will leave it up to your judgment for something like this, how much of it you do in the written work and how much of it you type it out. I will tell you this: if you simply say work attached here and only attach that, like, that's a really bad answer. I needed some point of reference that will allow me to attach a point of this answer within 20 minutes with the work that you attach that could be done after 20 minutes. So here, let me just type everything out. I think that's going to be the cleanest. So I'll say the second order time derivative of ext is, I'm going to use exponential representation because that's going to be much easier. So the ext divided dt. I know it's partial, but I'm just going to leave it that way and have dealing with the limitation of typing. So that's going to be minus. So with each derivative, I bring down a factor of I minus I omega. Minus signs cancel between two of those, but I squared give me a minus sign. That's the minus omega squared times, and nothing else changes. So it'll be just e of xt. The second order time derivative of, not time, x derivative of e of xt is this time xt dt dx. Oops, and actually said the second order, so it should be written that way, that way, that way, that way is equal to, and this time I'm bringing the factors of ik with each derivative. So I squared again gives me minus, and I get k squared, and the rest doesn't change, so it's x of e of x and t. Plugging these into the wave equation, we get minus omega squared times e of xt is equal to 1 over c squared times minus k squared times e of xt. So as long as c is equal to not square root, c is equal to k over omega, I think. No, c is equal to, I gotta do this. So canceling out things, you have omega squared is equal to k squared over c squared. Everything else has been canceled out. Solving for c is equal to so c over k over omega, I think. Yeah, okay. So as long as c is equal to k over omega, the wave equation is satisfied by the suggested form of e of xt. I guess I have to say complex version. And this is probably a little bit on the sparse side, but someone giving this answer, I would think, they probably understand the key things. They are just under time pressure and didn't write down things they felt they didn't have to. Okay, so that's part A. Part B, the photo below shows Newton's rings visible when. Yeah. By the way, for this photo, it's actually the planar side of the two lenses that's in contact. So if those plane sides were perfectly plane, then you wouldn't see any of these rings. Presence of these rings indicates that the radius of curvature is slightly different. Quality to explain the mechanism by which these rings appear. This is an example of thin film interference, where thin film is the quote-unquote film of air gap between the two surfaces of the lens. The light reflecting from the two surfaces of the two lenses touching each other. The light reflecting from the top surface and the light reflecting from the bottom surface undergoes different phase changes. The light reflecting from the bottom surface has additional phase shift due to additional distance traveled plus a potential pi phase shift from reflection. Additional phase shift. So at the locations where these different phase changes result in destructive interference, pi phase difference between two reflected beams. I'll just leave it there. Pi phase, or all the integer multiple of pi beams. You see dark fringes, bright fringes are seen, where these different phase changes result in constructive interference, 2 pi phase difference between two reflected beams. Alright, so that's the kind of qualitative explanation. The thin film interference would be the key kind of reference that would indicate, this person knows what they're talking about. Okay, thinking back to your experience of blowing soap bubbles and observing rainbow colors appear based on how these rainbow colors appear. So this is another example of a thin film interference. And I guess the way I would explain the rainbow colors is the thin soap bubble film does not have a uniform thickness, and depending on the location of the soap bubble film, either the red color around like 650 nanometer is closer to the constructive interference, or the another color like green 500 nanometer or blue 400 nanometer is closer to the constructive interference. Whichever wavelength is closest to constructive interference gives the color of the soap bubble at that location, and the change of the film thickness at different locations result in different colors. Different colors at different locations, resulting in rainbow appearance. If you somehow made the precision machined a kind of a film thing that had a uniform thickness, you wouldn't see rainbow colors. You would see one color, whichever one has constructive interference. Okay, how much time? 9 minutes. Oh, this must be easy said. I'm not using all my time. I know 20 minutes is not a lot of time. I have the benefit of, well, I wrote these questions, so I don't have to. My thinking time is a lot shorter because, again, I wrote these questions. In the days before Youngstown, yeah, this is called, yeah, Poisson spot. That spot there. This experiment is obviously done with a laser light, but I think they did this with like a sodium lamp. Yeah, when they observed the bright spot, that actually added to the wave theory of light instead of sinking it. Qualitatively explain how this bright spot appears in the center of the circular shadow and only in the center. So consider perfectly circular obstruction. Figure attached in attached work. So this is kind of, let me draw a side view. So side view. So I have kind of, this is my circular obstruction. It can be a sphere. It can also just be actual circle. It's just the precision is what matters. And imagine you have light wave incident on it. And you have to imagine kind of the front view, like perfect circle. Then with the light incident, what you'd have is, so basically with this circular obstruction, you have these points on the edge basically acting as a source of wave according to the Huygens principle. So when you are looking at a screen here, you are looking at, okay, at what point on the screen will these two constructively interfere? And it's more complicated than like a double slit because it's a whole two-dimensional shape. And one thing you can say is that at the very center of the shadow being cast by the obstruction, the distance from that edge to that center point is equal distance from every single point along the edge. So all these wave sources, they constructively interfere right in the middle of the shadow. So that's where you see this slightly brighter spot. Anywhere else, I mean, some of those might be constructively interfering, but not all of them. So any kind of constructive interference will be dimmer. So that's why only at the center. It's the only spot that's equidistant from every point on the edge. So it gives you that constructive interference. The center of the shadow is the only spot within the shadow that is equidistant from every point along the edge of the circular obstruction, which serves as a point as a new point source of wave according to Huygens principle. Did I spell Huygens right? Huygens. Oh, by the way, you shouldn't be Google searching while you're doing this because that's outside the resource. Let me not do that. According to Huygens principle, and being equidistant, all the light waves constructively interfere at the center. At any other point within the shadow, some of the light waves waves might constructively interfere, but many others won't. So the intensity is of the diffracted light is not as intense as it would be at the center, where all the light waves constructively interfere. All right, I think that's it. Let's see how much time I got. 4 minutes. Yeah, so let me attach that, and I think I'm done. Yeah, so this is a kind of qualitative question. This might be coming from my final exam questions, because I like to ask qualitative questions in the final. Because sometimes people focus on formulas, and you gotta do both. You gotta understand things from conceptual side. You have to be able to solve problems, work out the math. You can't let one overshadow the other. You have to be able to explain things conceptually, and you need to be able to work out the math when you need to. So, all right, that's it. And I guess I'll do the same thing with this. I will go get the model answers and make sure that I didn't miss something important. Let me go get the model answers. Okay. Here's the part 2. Oh, test student is the only one who's done it. All right, so yeah, all that. Let's look at the answer key. Yeah, you're just taking derivative. You can take it one at a time. I think you can take it all at once. Yeah, that's it. I don't think. Yeah. Yeah. And model answers more detailed. Which because I was typing, I didn't draw. I think it's fine. Air gap, yeah, thin film interference, yeah, and it has more detail, which I guess you could put it in unnecessary. It's a semi open-ended question. Here, colors, yeah, that, and yeah, variation in thickness, yeah. And finally, I swear I didn't see this. There's a kind of consistency here. Yeah. I wrote this solution many years ago, but certain things, I'm very predictable. I do certain things like the exact same way without realizing I am doing it the exact same way. Yeah. Okay, good. So I think that's everything for this question. So those are so far 2 examples or 2 demos of the freeform timed assessment. Good luck when you're doing it. Again, 20 minutes is a short amount of time. In that 20 minutes, focus on getting the answers down and your attached work. You can organize, modify, fix between when you finish your answer and when you attach your work using the add work button here.